List the following aqueous solutions in order of increasing boiling point. 0.12 mole glucose, 0.05 mole lithium bromide, and 0.05 mole zinc nitrate. All right, so with this problem is you're leveraging the fact that glucose has a Van Hoff factor of 1. So if you have a 0.12 mole solution, you have 0.12 moles of particles. Whereas with lithium bromide, you have a Van Hoff factor of 2. So if you've got a 0.05 mole solution of lithium bromide, you've got a 0.1 mole solution of particles. Zinc nitrate has a Van Hoff factor of 3. It breaks up into 3 moles of particles. So 3 times 0.5 gives you 0.15 moles of particles. So the one with the greatest colligative effect would be the zinc nitrate, right? Most particles going into solution. 73, using the data table 13.3, calculate the freezing point and boiling point of each of the following solutions. A 0.22 mole glycerol in ethanol, and 0.24 moles of naphthalene in 2.45 moles of chloroform. All right, so A. We're using delta T is equal to I times the freezing point constant times the molality. Delta T is equal to I times the boiling point constant times molality, right? So freezing point depression, boiling point elevation. So they gave me the molality of the solution. What I need to know is what the Kb value is for ethanol and what the Kf value is for ethanol, what its normal freezing point is, and what its normal boiling point is. So you get this on table 13.3. So with this information, you plug in the Kf value for ethanol, multiply it by the molality of the solution. The Van Hoff factor here is 1. And you get what the change in freezing point is, right? We take that change in freezing point and we subtract it from the normal freezing point, right? It's freezing point depression. So it's going to freeze at a lower temperature. Boiling point elevation, we multiply the molality by the boiling point constant, and we get how much you're raising the boiling point. So whatever delta T comes to, we add it to the normal boiling point of ethanol, and we get how much higher the temperature has to get in order to boil ethanol. All right, B, they didn't give us the molality of the solution, but they gave us moles of naphthalene and moles of chloroform. So if I use moles of chloroform, right, use the molar mass to get to grams, and use the definition of kilogram to get to kilograms of chloroform, I can divide into moles of naphthalene and get the molality of the solution. All right, now that I have the molality of the solution, I can go back to that table and look up what the normal boiling point is for chloroform and what its Kb value is, what its normal freezing point is, and what its Kf value is. And now I can use the molality of the solution. Again, chloroform, like naphthalene, isn't an electrolyte. It's not going to break apart. So multiply the molality by the Kf value. Subtract the Kf value from the normal freezing point to get how much the freezing point, tells you how much the freezing point is depressed, and subtract that from the normal freezing point to get the adjusted freezing point. Same with the boiling point. Multiply the molality by the boiling point constant, add the delta T to the normal boiling point to get the higher boiling point, right? The boiling point elevated. What is the osmotic pressure formed by dissolving 44.2 milligrams of aspirin in 0.358 liters of water at 25 degrees Celsius? Osmotic pressure, pi, is equal to the Van Hoff factor times the molarity of the solution times the gas constant times the temperature in Kelvin. So what is osmotic pressure? Well, we need solvent on both sides of a porous barrier. The rate of transfer of the solvent particles across the porous barrier is equal, right? So the levels of the fluids don't change. If I put a solute on one side, it obstructs these solvent particles from getting access to the porous barrier, and you impede rate of transfer of solvent particles across the barrier on this side. So what happens is you don't impede the other side, so you end up making the levels of liquid unequal, right? You end up building a pressure on the one side. So in order to establish the rate in one direction equal to the rate in the other direction, and get the levels back to normal, you got to apply pressure. So this is what osmotic pressure is. The pressure you'd have to apply to level or equalize the levels of the fluid on either side of the porous barrier. So in order to get this equilibrium of transfer of the solvent particles, the transfer of solvent particles equal in rate with a solute in there, I have to apply pressure, and that's what osmotic pressure is. All right, so we need to know the molarity of the solution, right? They gave me milligrams of aspirin. Well, I'd have to use definition milligram to get to grams, use the molar mass of aspirin to get to moles, and divide by liters to get the molarity. Once I got the molarity, I multiply by the gas constant, 0.0821 liter atmosphere mole K, multiply by the temperature in Kelvin. Kelvin cancels, moles per liter cancels, and I'm left with my pressure in atmospheres. If you don't like the pressure in atmospheres, right, it's too small a fraction of an atmosphere, you can convert it to millimeters of mercury and get what the osmotic pressure is for this system. Our fourth colligative property. Lysosome is an enzyme that breaks bacterial cell walls. A solution containing 0.15 grams of this enzyme in 110 milliliters of solution has an osmotic pressure of 0.958 torr at 25 degrees Celsius. What is the molar mass of lysozyme? All right, so I rearrange osmotic pressure, all right, so I can solve for the molarity of the solution, right, so divide both sides by IRT. I know what the temperature is, I know what R is. What I need is to have osmotic pressure in atmospheres, right, so they gave it to me in torr. So 760 millimeters of mercury is the same as torr. I convert to atmospheres. Now I can plug this into the osmotic pressure expression rearranged and solve for what the molarity of the solution is. All right, so molarity of the solution. They told me what the volume was, right? So get it in liters. So 0.21 liters multiplied by the molarity gives me moles of lysozyme. This many moles of lysozyme weighs 0.15 grams. So I divide moles into grams to get the molar mass. Lysozyme is a very large molecule.